So what this question is testing, and I could easily make this a multiple choice question, maybe I would. In this question, the first question, part A, asks you to calculate the mechanical energy of the pendulum relative to the floor when the bob is at its highest point. At its highest point, it only has what kind of energy? Only has potential. So is that a fairly easy calculation? Okay. What is the answer? So let's calculate that. Let's do part A together here. Okay? So on part A, okay, we know that mechanical energy equals the sum of an object's potential plus its kinetic. Well, we know at the highest point it's not moving. All of its energy is potential at that point. So the mechanical energy is going to be mass times gravity times height, which will be 0.25 kilograms times 9.81 times 0.25 meters. Okay? So if we punch all that into our calculator, okay, 0.25 times 9.81 times 0.25. Okay, so there's our mechanical energy at the highest point, 0.613 joules. What's the answer to part B? Keeping in mind that this is testing the idea of the law of conservation of mechanical energy. What's the answer to part B? 0.613 joules. Energy is conserved. It has the same amount of mechanical energy anywhere along the arc shown in the picture. All that's happening is kinetic is being turned into potential, and potential is turned into kinetic as it swings back and forth. Okay? That's exactly the kind of thing I would put on a unit exam. Question number 10 is calculate this. It's an easy calculation, right? That's a good multiple choice calculation, m times g times h. And then part B, the next question in line would be, what's its energy at the lowest point? And I'd have some other answers. I'd probably calculate what the potential energy at the lowest point is, what the kinetic energy at the lowest point is, to throw in some good distractor items. I'd throw in 0 to see if I catch anybody. Okay? And then I'd put in that same answer from the first part. That question requires no calculation. And if you understand the law of conservation of energy, that question only takes you as long as it takes to read the question. Okay? It should be pretty much automatic. Oh, right. Conservation of energy says that number never changes. Boom, I've got my next answer. Okay, does that make sense to everybody? Okay. All right, so part B, we don't have to do any extra calculation. It's still 0.613. Now, for part C, yeah, that does require some calculation. So does part D, okay? But not a lot, okay? Not a lot of calculation. How many people would like a little bit more time for C and D? Okay, I'll give you a little bit more time. Do I still need that 0.613 joules to solve part C? Yeah, I see people nodding yes. Yes, you do. Okay? That is my mechanical energy anywhere along the path that the pendulum follows. Okay? So if that's the case, anywhere along that arc, 0.613 joules equals the sum of the pendulum's potential and kinetic energies. In part C, they tell me they want to know the kinetic energy of the bob at its lowest point. Well, does it still have some potential energy at its lowest point? Relative to the ground, it does. Practically it doesn't, because it's not going to fall any lower than that, but from relative to the ground, yes it does. So, can I calculate how much potential energy it has at that lowest point? Mark, can I? Okay. So, if I subtract EP over to the other side, will that get me my kinetic? All right, so I'm going to go 0.613 joules minus 0.25 kilograms times 9.81 times 0.05 meters. Okay, that'll be my potential energy at the lowest point relative to the ground. All right, so 0.613. And we'll just put it in because now we're using it from part A or part B. Okay, minus 0.25 times 9.81 times 0.05. Okay, there's my kinetic energy at the lowest point, 0.490 joules. All right, everybody okay with that? Can I use that number to solve part D? Well, I don't know how I would solve part D without it. Okay, that's the kinetic energy of the pendulum bob at the lowest point, and that's what the speed of the pendulum bob depends on. So, what I can say for part D is, okay, that EK equals 1/2 mv squared. I know this number, it's 0.490. I know this number, it's 0.250. So all I have to do is isolate v. So EK divided by half of m, square rooted, will get me v. All right, so we will have then the square root of 0.490 joules divided by 1/2 times 0.250 kilograms. That'll give me the speed of the pendulum at its lowest point. So half of 0.25 would be 0.125. All right, so it'll be going 1.98 meters per second at its lowest point. Okay, is that still at its heart a roller coaster question? We still use the same concept to do it. That concept being EI equals EF. Okay, for a pendulum, its mechanical energy is the same anywhere along the arc. For a roller coaster, its mechanical energy is the same anywhere along the track. Okay, it's not changing unless they tell us there's some force that's doing work. Okay, everybody all right with that idea? Right, so it's a simple situation, and this is the kind of question like when people see just how little math is involved in it, it's kind of a facepalm moment. And that's okay, that's the purpose of showing you that question is sometimes it's just about understanding the concept and not about doing a roller coaster question where I've got all these formulas and I got to move a whole bunch of things and do a bunch of algebra. Okay, sometimes it's just about understanding the concept. That's the kind of thing that ends up as a multiple choice question versus a written response question where you got to do the whole thing, EI equals EF, and break it all down. Sure, I'll probably ask that. Okay, but I can also ask about that concept in a different way. This could be that different way. Okay. Okay. This is similar. I'd like you to try this one. Okay. Model rocket. Okay. The mass of the model rocket is 3 kilograms, and it's fired so that when it is 220 meters above the ground, it is traveling vertically upward, so straight up. Okay, at 165 meters per second. At that point, the fuel runs out. So that means no more work is being done after that point, right? The rocket engine can do work, but once its fuel runs out, this becomes a conservation of energy question. Okay, so from there, at that point where it's 220 meters above the ground and moving at 165 meters per second, calculate the mechanical energy of the rocket for part A. Okay, when it reaches the highest point, what will its gravitational potential energy be? And see how far above the ground is the rocket at its highest point. There may be a lot less math involved in this than you think. Okay, so for part A, it just wants to know the mechanical energy of the rocket at that initial point. Okay, well, as we know, mechanical energy is the sum of an object's potential and kinetic energy, and the rocket has both at its initial point. Okay, so we can calculate that by going basically m times g times height initial plus 1/2 mv initial squared. We know all of those numbers. Okay, the mass of the rocket is 3 kilograms times 9.81, okay, times its initial height of 220 meters. Plus its kinetic energy, 1/2 times its mass, 3 kilograms, times 165 meters per second, all squared for its kinetic energy. Okay, so if we punch all of that in, okay, so 3 times 9.81 times 220, okay, plus 0.5 times 3 times 165 squared. All right, so we're looking at, well, it's a lot. Okay, we're talking 47,312.1 joules. Okay, that's a lot, but that's our number. We would have 3 significant digits here. So 4.73 times 10 to the 4. Okay, so that's what we start out with for question A. Now, for part B, when it reaches the highest point, what will its gravitational potential energy be? Does this require any calculation? Okay, this is another example of a question that could be a multiple choice question. Okay, at its highest point, how fast is it going? 0. So it has no kinetic energy at that point. All of its mechanical energy at that point is potential energy. And that's a question that would be asking, do you understand a bit of projectile motion, okay, a bit of conservation of energy, okay, yeah, at its highest point, this is its potential energy, because energy is conserved, and as it goes up, it's going to convert its kinetic to potential. Now, for part C, how far above the ground is it? Okay, well, at that final point, its mechanical energy is all potential, so that would be m times g times final height. We know what that mechanical energy is because we already calculated it. We know the mass of the rocket. We know what gravity is. Okay, divide those two over to the other side, and we're looking for HF. So we would have 4.73 times 10 to the 4 joules divided by 9.81, whoops, sorry, not H, M, okay, times 3 kilograms. All right, so if we go 4.73, okay, E4, because I'm using an answer from the previous, so I got to carry over my significant digits, okay, divided by 9.81 times 3. Okay, it is 1,607 meters, 1 vertical mile above ground level. Okay, at its highest point. Everybody okay with that? Okay, so questions like that, they seem like they should have more to do. But if we really understand the concept, then there isn't actually that much to do, right? We didn't have to do all that much math, and that was the extent of the algebra we had to do, was divide both sides by mg, okay, for the second part. Okay, now, same idea. How fast is it going when it hits the ground? Do I know the mechanical energy of the rocket when it hits the ground? Yeah, it's 4.73 times 10 to the 4 joules. The law of conservation of energy says that number is the same anywhere along the path of the rocket, okay, until the instant after it hits the ground. All right, so we are talking about the instant it hits the ground. It still has that much energy, and since it's hitting the ground, all of it is kinetic. Okay, there's no potential because our height would be 0 on the ground. So all we have to do is say our 4.73 times 10 to the 4 joules equals 1/2 mv final squared. And I'm just solving for v final. I still know the mass of the rocket to be 3 kilograms. All right, so we're going to divide 1/2 of m off and then square root that, and we've got our v. Okay, so we will have 4.73 E4, okay, divided by half the mass, so 1.5, and then we're going to square root that. Okay, so when it hits the ground, it's moving at 178 meters per second. Okay, when you first read that question, it seemed like it should be more than that, like more work. Okay, again, as long as we have that understanding that EI equals EF, more than just this is the pattern I write down when I recognize it's a roller coaster question. If we understand it beyond that, okay, we can answer questions like this very quickly. Okay, like that's not maybe not a great multiple choice question, but that would be a great numerical response question. Okay, there's not a lot of calculating, but I make you put in the number, right? Something like that certainly could go that way. Okay, any questions on that one? All right, rather than do number 3, because it's very obviously a roller coaster question, okay, I would like you to try the pole vaulter question, question number 4. Okay, we are making some simplifications to the situation of pole vault, okay? But a pole vaulter with a mass of 56 kilograms wants to convert their kinetic energy of their approach, of her approach, into height, okay? What is the maximum height she can attain if her approach speed is 8 meters per second and her center of mass, which is what she has to get over the bar, is 0.850 meters above the ground? Okay, so we are getting an initial height here, right? Her center of mass, okay, that's usually kind of like right here. If we're like centering out where most of our mass is, it's usually slightly above our waist. Okay, so 0.850 meters above the ground. Okay, so her center of mass does have some potential energy to start with. All right, let's see if we can solve for how high she would go. Here's the simplification. I understand that in the real world, she would still have some kinetic energy horizontally to clear the bar. We're going to imagine she messed up and she went straight up and then came straight back down. Don't laugh. I've done that, okay? And I've seen other people do it. It isn't fun because it really hurts, okay? Because you're usually inverted at that point, and yeah, you come down right on your head. Explains a lot, doesn't it? Now that you know I've landed on my head from that far up. Okay, in the last couple of questions that we did, the mass of the person mattered. Okay, we had to use the mass of the person because we were being asked to calculate energies. What was their potential energy here? What was their mechanical energy here? What was their speed here? Okay, well, in order to do that, we needed to have the energies, which means we needed to have the person's mass. Do I need the mass for this question? What am I being asked to calculate here? A height. Knowing that I've got an initial point and a final point. I can solve this like a roller coaster question. Okay? Now, a few of you may have, just because we did a few like this, calculated her mechanical energy on the ground and then went and put that in to calculate what her height would be. Is that the same as saying this? Her energy on the ground is the same as the energy she has as she goes over the bar. Right? You may have done it in two steps. You actually calculated what EI was and then used it for EF. Well, I can skip that step by just saying, hey, they're equal. EI equals EF. Okay? I know that on the ground, she has a small amount of potential and a fair amount of kinetic because she's moving at 8 meters per second carrying a long pole. Okay? Not an easy trick. And then at the end, we assumed all of her energy would be, she goes straight up. How fast is she going at her highest point? 0. So all of her energy is potential. Yeah. Okay. So EP final. All right. So then I can go m times g times h initial plus 1/2 mv initial squared equals m times g times h final. Okay. Since I'm only looking for a height, okay, and I know those 2 points are equal, her mass is irrelevant. Okay? I can plug it in if I want, but I don't need to. Thus I won't, because I don't like doing extra work. Okay? I just want to calculate HF, so I'm just going to divide both sides by G. Now I've got HF, so 9.81 times 0.85, that was where her center of mass was, plus 1/2 times BI squared, okay, divided by 9.81. That's going to give me her final height. Okay, so 9.81 times 0.85 plus 0.5 times 8 squared, okay, divided by 9.81. All right, she's going to reach a height of 4.1 meters. Okay, having coached track and field, high school track and field for 20 years, I have never seen a high school pole vaulter, male or female, go that high. Okay, that is an impressive height, to say the least. Okay? In high school competition, I've never seen anyone use a pole longer than 3 meters. It would be really hard to clear a bar 4 meters and a little bit high with a 3 meter long pole. Okay, so this person is really, really good at pole vault. Okay? At the high school level, pole vault is high jump with a stick. Okay? I've actually seen competitions where the high jumpers were higher than the pole vaulters. Pretty sad. Okay? Now, pole vault's not easy. To say the least, you have to be really athletic to do pole vault well. Okay? It's not just about speed. You need really good core strength because you're practically a gymnast, part of the reason I wasn't very good at it. Okay? And you also need a fair amount of upper body strength as well, because you got to hang onto that pole for dear life. Okay? There's a lot of energy conversions that go on during the pole vault process. That's what part B is asking about. Okay? So what I'm going to show you now is a little video that shows pole vault, okay, in action. It's actually the quickest broken world record in Olympic history. Okay? And it's by this guy, I mean, he's been retired for a long time, but he was an incredible, the best pole vaulter who ever lived. Sergei Bubka. Okay? He was a Russian pole vaulter. Guy held the record forever. Okay? He was just really, really good. Okay, so if we're talking about energy conversions, thank you. Like you're running in and you have all kinetic energy. Okay? But as soon as you plant that pole, what do you do to it? The pole starts to bend. Are you doing work on the pole? You're definitely doing work on the pole. You are transferring your mechanical energy to the pole. The pole is storing that as elastic potential energy. It's changing its shape, okay? But it wants to go back to straight. Poles don't like to be bent, okay? So you bend this pole, and then when you get it to the, basically a horseshoe, okay, it starts to do work on you. That's the point where you have to be inverted, okay? It's also the point where bad things happen, all right? Believe it or not, a pole vault pole has two sides, a soft side and a stiff side. That's why it can bend the way it does. If that pole rotates in your hand and you plant it and it's the wrong way, it'll either bend out to the side, which will throw you in a bad direction, or if you have it completely upside down, it will simply snap. But it won't snap until you're fully committed and are upside down and have bent it as far as possible. That's when it'll snap. Okay, seen that happen. Didn't happen to me. Okay, but I've seen people who were strong enough, I wasn't, okay, to bend the pole enough to snap it. What happened to me is I got it to go out to the side, and then I got completely inverted, and then I realized, oh crap, this pole is not throwing me where I want to go. Bonk. Okay, I could never do it again after that. I was never able to pole vault again. I became like that high jumper video where the guy just bails and goes right underneath the bar. That was me. Just kept running under the bar with the pole because I just couldn't do it. Okay, just sometimes you can't get back on that horse. Okay, so in this case, we see a lot of changes in energy. Okay, you've got lots of potential in the form of elastic potential, then it does work, turns it back into kinetic, turns it into potential, you go back down, you fall onto the mat, potential into kinetic, do work on the mat. Okay, everybody all right with that? All right, we have a couple of minutes left here where we're going to talk about power really quickly. Here's the good news about power. There's no calculations for power. Okay? All you have to do is understand what power means, okay? And you'll be good. All right. Okay, so this is the last lesson, I believe, in your notes package, okay, if you have that. So, power, very simply, is the rate at which you do work, or how fast work gets done. All right, very simply, not that you'll ever have to use it, okay, but the formula for power is work divided by time. Okay, so the units are joules per second, or a watt. Okay, watts measure power. Okay, they measure the amount of work done in a certain period of time, okay, or the amount of energy given off in a certain period of time. So if you have a 60-watt incandescent light bulb, it uses 60 joules of energy every second. It's why we've replaced them with those LED light bulbs in your house that are like a 4-watt, okay, LED. Okay? They only use 4 joules of energy every second, which is a lot better than 60. By my math, about 15 times better. Okay? All right, so power is work divided by time. Here's the thing that people get wrong about power. Okay? These two identical 1997 Honda Civics, well, they're not identical, but they're both 1997 Honda Civics. One is the way you'd buy it on the showroom floor. Okay, had a 1.6 liter 4-cylinder naturally aspirated motor that generated a whopping 130 horsepower, okay, and could go from 0 to 60 in 2 weeks provided you were downhill with the wind. Okay, it was not very powerful. It was very efficient though, okay, but it was not very powerful. The other one, Vin Diesel and Paul Walker have done a little work on. Okay, they've got it all fast and furious out, okay, and it is generating far more power. Okay, now if we compare these two, okay, this one can get from 0 to 60 in 4 seconds. This one, 8 seconds. Okay, so which one's more powerful? They both have to get from 0 to 60, right? Okay, that requires a certain amount of work. Which one does it faster? Vin Diesel's car, okay, not driving Miss Daisy's car. Okay, Vin Diesel's car is the one that does it faster because it's more powerful. Does that mean it does more work? That's the part people get wrong. They both do the same amount of work. One just does it faster. Okay, so if you, for example, at home, when you dry your hair in the morning, you got your hair dryer, okay, I don't obviously need that, but okay, if you have hair and have a hair dryer, okay, there's usually a rating on it for watts. Hair dryers are usually somewhere between 1,000 and 1,500 watts. Okay, so if one person has a 1,000 watt hair dryer and another person has a 1,500 watt hair dryer, who dries their hair faster? The 1,500 watt. Does it require the same amount of energy? Let's assume they're identical twins with exactly the same hair, okay, and they both get out of the shower at the same time, okay, it's going to be perfectly the same amount of work, but one person is standing there with the hair dryer for roughly 30% longer. Okay? Do both of them do the job? Yes. Okay? A less powerful machine can do the same amount of work as a more powerful machine. It's just going to take longer. Okay, that's the key. A more powerful machine does not do more work unless time is a factor. Okay, now if I say to both of those people with the hair dryers, you only have 1 minute to dry your hair, okay, well, one of them isn't going to get done. Okay, it won't do as much work because it can't do it as fast. Okay, but if time is not a factor, it doesn't matter how powerful the machine is, they can both do the same amount of work. Okay? All right, so these two things are both hydroelectric dams. All right? That's a 1800 style water wheel, and that is Grand Coulee Dam. It provides electrical power to the Pacific Northwest. That's Washington, Oregon, and parts of Idaho. Okay? Can they do the same amount of work? Sure they can. If I run Grand Coulee Dam for 1,000th of a second and I run this water wheel for 1,000 years, yes, they can do the same amount of work. Okay? But one is obviously more powerful than the other. That's what power is. How fast can I do the work? Not can I do the work. Any machine can do the work. You just have to give it enough time. Okay? Everybody okay with that idea? That's the real kind of stumbling block around power, and that's the kind of question I'm going to ask. Okay, it's going to surround the idea of power is how fast you do work, not how much work you do. Okay, can two machines that are not the same power do the same amount of work? Yes. Okay, but one is going to do it faster. Okay, everybody all right with that? Okay, also understand the units. Units for power are watts. That's a joule per second. Okay. All right. Questions on power? Okay. Tomorrow we're doing a lab. Okay. We're going to do a lab where we're looking at how efficiently potential energy is converted into kinetic energy for, surprise, surprise, a cart going down a ramp. Okay. We've got a lot of experience with using those carts and those ramps, so we're going to use it again. Okay. But this time from an energy perspective. Okay. And then Friday quiz. Okay, the practice quizzes you should do, 8, 9, and 10. Okay, that's going to be all work energy, conservation of energy, that kind of stuff. And then obviously unit exam is Monday. Okay, I will try and get those marked as quickly as possible. If you would like to come back and get your quiz at the end of the day on Friday, okay, I will have them ready. You can come back and get it at the end of the day. Okay, I'll try to get them marked really quick. Then maybe come back to you before class is over if you guys are real fast. Okay, all right.